Hello guys, good morning everyone. Sorry for being slightly late. Let me join the screen, the Zoom chat from the other screen, then we do definitely start. So hopefully you all enjoyed the last week of studies and you successfully trained with your class teachers the covariance and correlation methods and all of these methodologies. Hopefully you're doing good. And so we could move away from all of the stories and topics that we discussed last Saturday. And hopefully we could start with a completely new story related to the to the continuous distributions. And this is going to be discussed by today. So last week we slightly touched this area and presented the idea, the core of a continuous distribution and continuous random variable. And what I'd like to do today is to elaborate all of the properties of these distributions, and then we will present one of the most popular continuous probability density function. All of that is going to be discussed today. To remind that a midterm exam is scheduled on the 23rd October, and it's going to start at 10 a.m. So you have to be by 9:30 in order to have a seat on the allocated place. Or going to be the allocation list. The midterm is going to be conducted at two rooms, R201 and R206. The allocation list where all of you are supposed to be allocated is going to be sent by the Telegram channel. And the exam starts at 10 a.m. and terminates at about 12 a.m. So you are going to be provided with two sections. The first of them is multiple choice section, where you'll have 10 questions with multiple choice answers. The three response section has 4 problems, and it is the solution and the solution path that's going to be scored. I'm going to share the past papers. So past papers of 2020 and 2019 will be published next week at the Telegram channel. And the plus today, the 5th homework is published as well. And you are supposed then to submit all of the homeworks, the 4th and the 5th by the last Saturday. So these are all the news that we were supposed to share each other. Now let's move on. Now, as we said last week, the continuous random variable does differ from discrete one. Well, discrete random variable has a finite number of outcomes. So say, for example, a die. It might be the outcome of a die is either 1, 2, 3, 4, 5, and 6. So this only 6 outcome list you may have, and it's pretty finite. While the continuous random variable of those variables that has infinite amount of outcomes, like the temperature. If you do forget about all of the physics assumptions, we may say that temperature could be from minus infinity up to plus infinity. And, depending on the equipment you use in order to measure the temperature, it might be, it may be evaluated as precise as it is possible, and it could be a real number. The same story is about the time. If you measure the time that you wait before the metro, comes to the station, or a bus, or till the end of the lecture or the end of the exam, it could be called as a continuous random variable as well, because the time may be measured within the infinite amount of accuracy. And actually, the accuracy of the evaluations does depend on the equipments only and the assumptions you do at your model or your computations or even evaluations. So these examples, they illustrate the difference of discrete random variable and the continuous random variable. And the key, to recap, is actually that now your variable is measured within the real space, all right, within the real line. While it was the natural numbers at the very beginning, now it is the real one. And actually, what you should care about is that discrete random variable is always limited by the finite amount of outcomes, while the continuous one has the infinite one. And we said that it's pretty impossible to apply the probability measure that we used before. So let me say the following. A couple of weeks ago, we've been developing some probability density functions and probability distribution functions of the discrete random variables. And we used to say that you need to measure a probability of, say, random variable A equal to 5. And you've been developing some distributions, some models, and all of that in order to be able to calculate this probability. And you see, if we discuss the discrete probability, then we used to say that a discrete probability could be estimated as a fraction of the number of good outcomes divided by the total number of outcomes. And actually, this fraction gives you what the population probability stands for. But here is the problem. If you do apply the same story to the continuous random variable, then we fail to do that. And the reason why we fail to apply the same intuition that is written at the bottom of your screen now is because the total number of outcomes associated with the continuous random variable is actually infinity. Let me say it again: the total number of outcomes associated with the continuous random variable is infinity. And if you recall your calculus skills, what happens if you divide the constant number by the infinity? Well, it goes to 0. Well, as a result, all of the probability at point, the probability of the precise outcome, tends to be 0, given that your random variable is continuous. And this is the reason why we should, or we must, introduce the concept of cumulative distribution function in order to be able to describe the continuous random variable in precise. So by saying cumulative, I do suppose that I'm going to sum up some of the probabilities. So basically now you should be able to differ two possible states: the probability of the precise outcome and the probability of an event that your random variable x capital is lower or equal to some x small. Well, that tends to be probability distribution function, while the probability that x is lower or equal to x small is a cumulative distribution function. All right. And voila. So now, once we say f capital of x small, it does mean the cumulative distribution function, basically probability of an event that x random variable x capital is lower or equal to x small, and that is actually defined as a sum of probability distribution functions. So here you have a CDF function, and here your PDF function is written. So to simplify, the CDF is the sum of PDF across all of the outcomes that does formulate these event. And the random event I am evaluating is actually that x capital is lower or equal to x small. What is highly to be important, what's highly important is that the definition that I presented to you right now was actually related to the discrete random variable. And the CDF is applied, may be applied to both of random variables, I mean to discrete and continuous as well. And while we are talking about discrete random variables, the CDF is then defined as a sum. While once we move to the continuous case, this sum is actually replicated by the integral. And the intuition I'm trying to highlight here to you is actually the following. Look, we spent the previous month in order to get into the discrete case. And now we are going to the continuous random variable case. All of the formulas that we used before, all of the methods, all of the modifications are going to be absolutely the same. They are going absolutely the same. But the key difference is that now that we are going to replace all of the integral, all of the sum, all of the additions and sums. Oh, wow. That's strange. Basically, we are going to replace all of the sum by the integration procedures. And actually, the integral may be treated as a continuous analog of this sum. As a result, we see that the continuous definition of a CDF, or basically CDF, of the continuous random variable is equal to the integral from minus infinity up to x small of the PDF of the f small. Here's your CDF, here's your PDF. So what I do integrate from minus infinity up to x of all of the probabilities of all of the PDFs. And actually that gives you the definition of the CDF. All right, so as I said, all of the formulas that we used before stays fixed. The only modification we do, we replace all of the additions by the integrations. All right, and actually, if you think about the continuous definition of a PDF, then you may care about the properties that your probability density function should possess. I mean, look, if you recall the definition of the probability that we introduced before, I mean the axioms of Kolmogorov, that probability is always positive or 0, is always less or equal to 1, and it should be located from 0 up to 1, and the sum of all of the probabilities across all of the outcomes must be totally 1. Well, the total sum must be 1. Actually, the same happens with the continuous probability density function. And the f small stands for a probability density function of the continuous random variable. So it must be greater or equal to 0. The total area under f small must be 1. So integral from minus infinity up to plus infinity should be equal to 1. But since f small is no longer a probability at the precise point, because you may recall the example that the probability of being equal to a precise number in case if you are working with a continuous random variable tends to be 0. Again, if you are playing with the continuous random variable, the total number of outcomes is infinity, and the probability that your continuous random variable equals to, say, 5 is 0. Well, as a result, the f small may be greater than 1. It may be greater than 1. So only one assumption, only one axiom is violated here, but it does not matter because we cannot no more longer apply the probability density function to model the continuous random events, but we are going to apply the CDF function. Let me write the following. Here I was saying two terms about discrete random variable and the continuous random variable. A probability at point and the probability that x is lower or equal to some threshold number. So if x was discrete, I was saying probability distribution function. If x was continuous, then I say probability density function. And actually, that's highly important because density is no longer a distribution, and it means that density does present some properties of the probability, but you cannot apply some distribution to play with that. So it's no longer the main quantity of the likelihood that we are going to evaluate in order to describe the properties of random variable. But speaking of a continuous random variable, it is a cumulative density, or sorry, cumulative distribution function. And actually, this same term is even applied to the discrete random variables as well. So here, how you could distinguish with the functions in order to realize what kind of variable we are playing with. Let me be honest. Speaking of the discrete random variable, the probability distribution function is highly important. It's much more important because it's easier to be modeled, because it's more informative. And you know, all the binomial distributions, geometric distributions that we discussed before was actually about that. While the CDF is more appropriate form to describe the continuous random variable state. All right. Yeah, of course, as we said, the values of the density function is no longer a probability at the point, so it just describes the concentration of the probability, but it's no longer a probability of the precise event. And actually, we cannot discuss the probability of being at point if we are working with a continuous random variable. It may be, well, it tends to be 0 as a result, and therefore we can no longer apply the PDF concept in order to describe the probability of the precise outcome. But instead, we can evaluate the case of we can model the cumulative value, the cumulative distribution function. And we said that the cumulative distribution function of a random variable x with a threshold a small, by definition, it is a probability that x is, lower or equal to a small. And as we defined it, it is an integral from -infinity up to a of the PDF across all the possible outcomes that are located from -infinity up to a. well, then the probability of X being greater than A and smaller than B could be defined. And actually, the problem is that this probability will be totally equal to the probability whether X is equal to A or X is strictly lower than B, or X is strictly greater than A and strictly lower than B. So that is gonna be the integral from A up to B of the PDF f of X dx. And hopefully, if you imagine the calculus of integrals, you'll see that here you have a point A, here you have point B, and if you do know the probability of being lower or equal to B, and you subtract the probability of being lower or equal to A, then you get, so this stands for the pink value, this stands for the green value, and the probability that you are looking for, the probability of being from A up to B, is actually this value. So this is kind of simplified geometry of a CDF. And if you subtracted them, then you get the statement that your random variable is located from one threshold, I mean from A up to B. All right, good. We have proved that, and yeah, please.
Yeah, the question is very simple, but why do we have such a definition for a probability? Why is it an integral?
Because we need to sum across all the possible states, and given that the difference between 2 points that you want to sum tends to 0, according to the Riemann theorem that was proved. So basically, if you go into the Riemann's theorem that says that the sum of functions.
This is clear that if we sum, yeah, it's an integral, but why do we need to sum? Because we can't calculate the probability in particular point because we will get a constant by infinity and it will be 0. Is it the only explanation?
Oh, actually, no. Actually, no. So as I said, the Riemann statement claims that this goes to the integral. All right, so this is clear. You discussed that at your calculus, and no big deal about that. Now we go to the discrete case. Well, here's your probability, and here's your outcome. While we've been doing the discrete case, we knew that we have, say, 3 possible outcomes. According to the definition of the probability distribution, we knew that P1 plus P2 plus P3 must give you 1. Well, because this is the axiom of the Kolmogorov, where we say that the total sum across all the possible outcomes must be 1. So this kind of axiom, and this cannot be negligible. Then we go to the continuous case. And what happens with your random variable if you are saying that it is no longer discrete? So here it was discrete, and here it is continuous. Well, obviously, you have the opportunity to split any interval within the infinite accuracy as you wish, and therefore you have a line. Well, it may be any curve you wanna. We do not discuss the curvature of this line, but you have a line. It means that every outcome from 1 up to 3 may be allocated to the probability. It may be allocated to the probability. And well, all right, so let me say that I may pick a point 1.1. I may go to that line and claim that this is the probability of that outcome. Before we go into the intuition of that, I must satisfy the axiom of the Kolmogorov, and I say, look, I need to sum across all of the possible outcomes and claim that it is one. But as we said, given that I have the infinite amount of points, the distance between them goes to 0, and that converges, according to the Riemann's theorem, to the integral definition across all of the observations that I have, and I claim that it must be one. Well, as a result, we replaced, because of the continuity, we replaced the addition by the integration. But here's come a trick, and here's come the moment that you were asking about. Look, I proved that the area under the probability distribution function is 1. So basically, the axiom of the Kolmogorov is totally satisfied, no big deal about that. What happens if I wanna measure a precise probability? And once I try to apply the probability of being equal to a precise number, well, it tends to be 0 because of the definition that we recalled at the very beginning. And it appears that the switch from discrete to continuous state claims that this is no longer a probability at the point, but it is a density of probabilities. So what we could say is that if I have sort of a horizontal line, then these values are equally likely. So I don't know the probability that this or that value happens, but if I had a horizontal line, then I would say that, look, although I don't know the probability of these outcomes, I may say that that and these numbers are equally likely to happen. And actually, this is the reason why it becomes a density. Does it make sense? Hopefully.
Yeah, now it's definitely more clear. Thank you.
Yeah, you're welcome. All right, so we practice a little bit the Riemann's definition of the integral, and I love calculus, and I suppose that you are calculus masters, because look, you are doing calculus for 2 years. You must be calculus experts, well, hopefully. But what makes the statistics fun here is that we are going to discuss a lot of calculus tricks. This is going to be very this is going to be sort of bread and butter for us to do all the modifications. And actually, the statement that you see right now on the screen may be proved in an alternative way compared to what I showed you before. So I may say, look, the probability of x being equal to x small, this could be presented as a probability of x being greater or equal to x, lower or equal to x. And this is an integral from x small to x small of the f of x u du. But as you know, once the boundaries of the integral are equal, according to the definition of Riemann integral, it is 0 by the definition. And this is kind of alternative proof that may be used here, but it's pretty trivial. All right, and here's the very important point. So look, you had a very good question before, where we draw some pictures, and I was presenting you the probability density function, while this is a cumulative density function. So here is the difference. The probability density function may be intuitively treated, it might be treated as a proxy of the probability point. Although it is not a probability point, but you may treat that to simplify the imagination, while the CDF is a probability of being low or equal to some threshold. And let's say here we have 7. You want to know the probability of being lower or equal to 7. Well, then you integrate from 0 up to 7 your probability density function. And this appears to be a density of. So this is a density function. And that is going to be evaluated here. So this is your value. Well, you may say that the total area was about 0.3, and the area under the curve here equals to 0.3. That is actually written here. So what you may understand now is that because of the probability density function being always non-negative, so it's either positive or 0, the CDF function is increasing function. So it's either flat or increases. It is always positive. The f of an empty set is 0, and the f of omega is 1. So basically, if you calculate the CDF function of a maximum possible value of your random variable, then it's obviously 1. So it increases from 0 up to 1 by the definition. All right. Any questions here?
One question. You've described cumulative distribution function in the header of this slide, yet you've written cumulative density function.
Oh, yep. Yeah, that was my typo. Thank you very much. Yeah, there was a typo. Yeah, thank you a lot. And now we have a pretty patriotic statement because one of them is written with blue, another with red, and the other is blue, is white. So yeah, pretty patriotic. So do you recall the flag of Russia? So it's a white, blue, and red, I suppose. Is it? Or they should be flipped. Yeah, I'm bad with that. Anyway, let's go to the next area. And here are the main formulas that we had so much before. We introduced with you guys the expectation, and we said that the expectation is the sum of the probability multiplied by the outcome. If we go to the continuous random variable, the expectation then is evaluated as the integral from -infinity up to +infinity of an outcome multiplied by the PDF. So this is your PDF. This is a case of discrete random variable, and this is a formula of the expectation of continuous random variable. The same trick happens with the variance as well. Well, we could say that the variance is an integral from minus to +infinity, x minus expectation squared multiplied by the PDF, and that's it. For you to highlight, the expectation of x squared is an integral of x squared multiplied by the PDF dx. And basically, if you have the expectation of the f function, the f is not a good function. Let's call it function h. Then it is an integral from -infinity to +infinity h of x multiplied by the PDF dx. And here you have a continuous random variable. So all of that is kind of a continuous analogs of of the metrics that we introduced so much before. All right, and the same formulas are actually the same interpretations are applicable here. I mean that, look, we do know the way how expectation, the variance may be treated, and it's not a big deal for us. What is modified now is that currently we say that the random variable may be continuous one, and that's why we are evaluating all of the computations with within the integration procedures. Evolve. The same properties of the expectation variance are applicable here. So still, the expectation is closed under the affine transformations. I mean the addition and multiplication by a scalar. And if you have ax plus b, then you may extract your expectation as a times expectation plus b. The same modification is applied to variance, but the constants addition does not make any shift in terms of variance, and the multiplication by scalar increases your variance squared. The expectation of x times y gives you the multiplication of two expectations, but this works for independent random variables. So why does it work for the independent variables? Well, if the two random variables are independent, then obviously their correlation is zero. And hopefully you recall the definition of the correlation. It is the expectation of the multiplication minus expectation of x times the expectation of y. And if it is zero, then that formula does work out. The general case of the variance of sum, we discussed that. Here must be plus actually, sorry. Oh no, I'm very sorry, my bad. It should be plus, yeah, sorry. All right, good. No typos more. And let me present you the first, most simplified, but very informative continuous distribution. So here's your first continuous distribution. That is called a uniform distribution. And the uniform distribution describes and models random variables with equal probabilities. So it's called uniform because all of the variables have the same probability to happen. And this may slightly kill your imagination, but hopefully if you survive, then you will definitely realize all of the properties and all of that. So look, the framework of this distribution is the following. You have random variable that is bounded by A and B. So you have two boundaries and your probability and your variable exists from A up to B, all right? It's never lower than A, it's never greater than B. And you know that every outcome from A up to B has the same probability to happen. Well, as a result, you say, look, the total sum across all of these probability, across all of these outcomes must be 1. Then we see, look, here's the probability density function. It is constant. So, well, as we said, all of the outcomes have the same, it has the same probabilities. So it is integrated from A up to B, and it must be 1. Well, then we get Px from A up to B. So it's P times B minus A. And then P equals to 1 divided by B minus A. And here what is written here. All right. If you want to practice the expectation variance calculations, you will definitely derive this. It's not a big deal. It could be done within a couple of the integration procedures. Very fun to do that. So you may use this as a practice for you to evaluate all of the expectations and variance integrals. But here, if you think that you captured the core of this probability distribution, of the continuous probability distribution, then let me show you one example that will definitely makes your imagination work. Before I show you an example, I do recall that a probability density function does not describe a probability at point, but it describes a density of the probability at point. All right, so do not treat the PDF as a probability at point because we are working with a continuous random variable. Now, an example. I have a random variable X that has a uniform distribution and it is located from 0 up to 1. Then let me draw a graph of the PDF. So I start at 0, it goes to 1. And what my probability density function value stands for? Well, the PDF is 1 divided by b minus a, and it is 1. And here's the fun. I have infinite amount of outcomes because my random variable is continuous, located from 0 up to 1, and every of them has the same probability to happen. But actually, I don't know the probability of them to happen. What I know is that their density is always 1. That's fun. If you want to evaluate the CDF, well, the CDF is actually an integral from 0 up to x small of the PDF dx. And actually, here you may ask me, why I'm not writing the minus infinity here at the bottom as I presented at the previous formulas? Well, I'm not writing the minus infinity there because I know that the smallest value of my x is 0. And here from minus infinity up to 0, x does not exist. Well, then you get PDF times x. Oh, sorry, I'm not right. I'm not allowed to write here dx. It must be du. Here is u. And I get PDF multiplied by x. And it is x minus 0 divided by b minus a. Well, if you write the CDF function in a more detailed way, then you get that it is x minus a divided by b minus a for any x from a up to b. If x is lower than a, then f is 0. If x is greater than b, then f is 1. All right, so here is your function. It is written here. And this is one of the most simplified continuous distributions that's still pretty widely used. And it's pretty basic. So it said that all the outcomes have the same likelihood to happen. Well, you know, it's good, but it's quite a simplified assumption. Although, if you think about more appropriate distributions, we may create a bunch of them. I'm not going to discuss now the exponential distribution, but it's another analog. It's another continuous distribution. This is going to be discussed in details in second module. All right. But this is kind of an example of another probability distribution. And now what we care is actually about the PDF and the CDF. What does these graphs demonstrate us is actually the likelihood and the probability of the outcomes. Well, if you look on the PDF here, Now you know that it is a density. It's not a probability. But what you know is that you may compare PDF values by itself. And you see, the smaller value of X I have, the greater probability density is. And then you say, I don't know what exponential distribution stands for, but these two graphs tells me that the greater probability is associated with the smaller values because of the exponential distribution. And the greater values has smaller probability tends to 0. So basically, the exponential distribution is such a distribution that assigns the greatest probability to the smallest values. But if X increases to plus infinity, the probability density dramatically decreases to 0. And this is one of the properties that is usually applied. But speaking of the real life, well, if you think about any continuous distribution, you may see that, look, this is pretty exotic, and we love that. We'd like to get into that and be fully with a full gun of these PDFs functional stories. But if we think about real life, I tend to believe that the greatest probability of my random variable should be associated with the expected value. Because look, I have the random variable and it has some probability distribution, and say that someone claims you that the expectation of the expected value of this random variable is 4. Well, I don't know how he or she estimate that, but you were said that it is 4. Then what you are going to tell? Well, you're going to think that the expected value is what I supposed to see on average. If I run the experiments many times, if I measure my random variable many times, then I suppose to see the expected value on average. And this intuition moves us to a very nice model that was developed by Gauss, the same mathematician that presented the linear algebra that you love a lot, and you were studying at your first year of studies. So again, the core of what we just said is that we think that it's going to be right to say that the maximum probability should be assigned to the expected value. Why so? Well, because if I run the experiment thousands of times, I do expect to see the expected value on average. And this gives you the normal distribution. The normal distribution is sort of an iPhone at the world of distributions. It's the most popular distribution. And during this rest of the lecture and the next week, I'm going to explain you and highlight you why the normal distribution is the god of the distributions. It was developed by Gauss, and he derived a PDF function that gives the intuition that we just discussed with you. If you have the expectation equal to mu, the maximum density, the maximum probability density is going to be associated with a case where X is equal to mu. It's going to be the most likely outcome. Under the assumption of the normal distribution, your random variable exists from minus infinity up to plus infinity. And the PDF function is such a beautiful function that is written here. So it's 1 divided by square root of 2 pi sigma squared times the exponent that is powered with the fraction x minus the expectation squared minus divided by 2 sigma squared. So this is a probability density function of the normal distribution. All right. Now let me do the following transformation. So I say that a random variable y equal to ax plus b has an expectation equal to a exponent x plus b, and the variance of y is a squared times the variance of x. So these transformations been discussed before, and we trained them a week ago. Now say that x has a normal distribution with 2 parameters. And actually, what I must explain and highlight now is that every probability distribution function, has a parameter. If you recall the Bernoulli's case, then we had the probability of success. If you recall the binomial distribution, there we had total number of trials and the probability of success. If you recall the uniform distribution, the parameters of that distribution were the boundaries where your random variable exists. And the normal distribution has 2 parameters. The first is expectation, mu in my case, and the variance sigma squared. And for example, the exponential distribution that I didn't present to you before, but we slightly touched it, has some strange parameter lambda. It's called frequency. We will discuss that. We will discuss the exponential as well, so don't be sad about that. Anyway, x has a normal distribution with 2 parameters. If x is normal, then y is normal as well. And the parameters are actually, well, they are modified accordingly to these transformations. So here's the expectation, and here is the variance. Now let's do the following. Let's say that A is 1/, sigma, and B is minus mu divided by sigma. So your y was ax plus b, then it is 1/, sigma times x minus mu divided by sigma. So actually it's x minus mu divided by sigma. And then if you apply these transformations, you get that here you'll have 0 and this is 1. Now let me explain what this all stands about. If x said to have a normal distribution with 2 parameters, mu and sigma squared, then the random variable z transformed as x minus mu divided by sigma will have a distribution that is normal with 0 mean and the variance 1. This is called a normal distribution, and that is called a standard normal distribution. So here we made a transformation that's called a Z transformation, and the Z transformation is such a modification that allows you to generate a standard normal distribution out of a normal distribution overall. So this kind of simplification of the problem. And it says that does not matter what kind of parameters you may have at the very beginning. So no matter what parameters you have at the very beginning, I mean mu and sigma squared, within the z-squared transformation, you may derive a standard normal distribution always. So it may be done always, does not matter what kind of initial distribution you have. No big deal about that. All right, that's kind of genius. That's a miracle. Why? Well, because if you imagine that you were living in the 18th century, so imagine 1755, for example, no electricity invented, a pen was not yet invented, so you write on the scratch of paper, you have no computers and no mobile devices. And what you even calculator was not invented. And you need to be able to model any problem. So what Gauss and Lorentz, these two mathematician geniuses, they realized is that the normal distribution is such a great distribution that it is the only one that could be transformed to the standardized way within these basic transformations. So the only I need to do is to apply the z-score transformation that's supposed to subtract the expectation and divide by the standard deviation. And that makes my variable being standard normally distributed. And the reason why these, and here are these two geniuses, well, except Lorentz, De Moivre does made a lot of, and the Gauss made the final part of the job. So to explain why it is important, look, you may be given with the question, could you please estimate the probability that X is bigger than 2 and less than 3? Could you please explain evaluate the probability that X with a standard normal distribution is greater than 2 and less than 3? What these guys did, they took the standard normal distribution that has 0 mean and 1 variance. They grabbed this PDF function and they estimated all of the integrals. Yeah, that's a nightmare. Living 250 years ago, without any machines and personal computers, or even a Macintosh, a calculator, these two geniuses grabbed these two PDF and the CDF functions, and they calculated the table of the normal distribution. So they did that by hand. 2 centuries later, now these scientists recalculated all of these outcomes with the computers, and the shock was that Gauss and De Moivre made no mistake. So the standard normal distribution table probability was absolutely correctly evaluated almost 3 centuries ago. Now let me explain how these values could be read. Here, this is a distribution, these are values of a CDF. So a CDF of Z, let me call it F. And let's grab a number, for example, minus 1.03. It is a probability that Z is lower or equal to 1 minus 1.03. Here I go first within the column, and I find a value that stands for the first 2 digits. This is minus 1, 0. So I need to know the full line here. That's what I'm looking for. The last digit is actually found within a column, and then I look into that column. The number I'm looking for is located on the intersection of the row and the column, and it is 0.1515. So about 15% chance is that a standard normal random variable with 0 mean and the standard deviation equal to 1 is gonna be less than minus 1.03. And these numbers may be captured from the standard normal distribution table. I'm going to share this table with you at the Telegram channel, and you are going to be practicing a lot about that with your class teachers. The shock is that the standard normal distribution, the standard normal random variable, although it lives from minus infinity up to plus infinity, the probability that it's lower than minus 3.5 or greater than 3.5 is about 0, as you see here. What is highly important to be claimed is that the standard normal distribution is symmetric. And if I was looking for a probability of minus 1.03, so this tail and that tail, they are totally equal. I mean that the probability that Z is lower or equal to minus 103 is equal to the probability that Z is bigger or equal to 103. And actually, because, yeah, please. I'm sorry. That's not fun. Really, that's not a fun joke. What I'm gonna do within your exam, you will enjoy the exam. Yeah, you have a question?
No, I don't. Sorry.
Well, that's not fun what Adam is doing. All right,
I don't think
then the
it's
exam gonna be. Well, probably he may need to do that. Anyway, let's go back.
the lack of sleep that's doing this to us.
All right. Anyway, let's go back to the example that I was showing here. As you know, the probability across all of these outcomes is about 1. And this event of being greater than 1.03 and the event of that. Adam, could you please switch off the microphone? It would be very kind from your side.
Can't you mute a person?
Well, I am doing that, but Adam is switching off the microphone. I think it's not going to be good to ask him to lead, but let's keep this in mind. Anyway, I was about to tell that event and this event are complementary event, as hopefully you agree. And then the probability of being greater than, of the probability that Z is greater than 103 is 1 minus a probability of Z being lower or equal to 103. All right? So these kind of modifications of these probabilities that you may need to know. And here might be a question. Look, I give you half of the standard normal table on. Could you please help me to evaluate the probability that Z is lower than 2? You say, look, we are smart enough and we know that standard normal distribution is a symmetric one. Then this probability is totally equivalent to the probability of Z being greater than -2. Look, this is the same trick that I did here in these first 2 columns. This probability is actually 1 minus the probability of Z being lower than -2. And the -2 OO stands here. So it's 0.2, oh, sorry. It's 0.0228. Well, if I'm doing all the evaluations correctly, it's 9772. And here you got it. So this is the way how that table could be could be evaluated. Although I would agree that nowadays the Python library is available to you guys, and you have a very powerful phones and the calculator as well. If you and because of that, these tables seems to be quite weird and prehistorical. Although if you said that, I would definitely agree. This table was a breakthrough 3 centuries ago. It was a breakthrough because it helped a lot to evaluate all of the probabilities. It helped a lot to measure the probabilities, the values, the likelihood, the chances. And all the mathematicians were extremely happy to play with this table. Actually, this is the reason why we are studying this table as a part of the history of science, of the statistics and math. And being honest, the only case where you are going to be working with these table are going to be the exams and the UL examination as well. There are problems that are designed to do some transformations and capture the right number out of that table. But speaking of real life, friendly speaking, I should be fair with you. You are not going to open this table in real life because all of these numbers are implemented into your Python notebook or any environment. But still, it was a great breakthrough in science. Why it was? Actually, the genius is that it's not only standard normal distribution that could be evaluated with this table, but any normal distribution that could be evaluated. Why? Because, well, because of the Z transformation. If you do make a Z transformation, any normal distribution is converged then to the standard one, and you may play with your table, and that's it. All right. Going back to the graphs of normal distribution, I would like to demonstrate this nice picture in order to explain the intuition of two parameters. So the first parameter stands for the expectation, and it shows the point of maximum of your probability density function. So it demonstrates the peak of density. If it is greater, then your distribution shifted to the right. If it is lower, then it is shifted to the left. And obviously, the standard normal distribution is the maximum of the standard normal distribution PDF function is allocated around 0. While variance stands for the accuracy and for the fluctuations. The smaller variance you have, the taller is your distribution, and the greater variance you have, the wider is your distribution. So here, you may compare two normal distributions with a 0 expectation, but here I have smaller variance. Therefore, a lower amount of outcomes is actually covered by a significantly positive probability. While under the assumption, of variance equal to 9 gives you the cover to a greater range of the probability outcomes. And voila. So actually, because of that, and because of this illustration, some of the mathematicians claim that variance does present the accuracy of evaluations, and it may be called as a risk. Well, sometimes if you model, say, a stock price return, your daily return from stock price trading, the smaller variance your random variable has, the more confident you may be about your return, because you know the deviation is pretty small, so 1 is pretty small, And well, you either get 1 or you may get -1, but you are pretty confident about your return. Although the case with a variance equal to 9 gives you a great range of fluctuations, and then you see that the range is pretty huge. It's pretty huge, and you may either get +8 or -8, +9 or -9. As a result, you have greater risk to capture the lower values, and you are less than confident about the outcome you will observe. So this kind of intuition behind these two parameters. All right. Well, I suppose that this is it by today. Yeah, if you have any question, feel free.
So in this picture, shouldn't the what's it called, the fair, like we have 0, 1, we have 0, 9, right? But then the purple graph,
Yeah, you're right.
be 5.
You're right. It should be 1 here.
Yes,
it should be 1 here. Yeah, thanks a lot. That's my typo. Well, I had a lot of typos today, actually. Well, hopefully that's all with my typos for the next lectures, hopefully. Anyway, the next classes are going to be allocated to practice the normal distribution table. I am going to share these table I had on the slides with you. And let me give a hint. To capture a calculator by your midterm exam, you will definitely need it to play with some numbers. All right. Anyway, the next lecture that's going to be next Saturday, is going to be spent to practice the previous exams. And I'm going to solve some of the past papers and give some introduction to what you may expect or should not expect, or you may get being unexpected at your midterm examination. Anyway, let me wish you to enjoy your weekend. Enjoy
Sorry,
your
may I ask a question?
Me too.
Yeah, feel free.
Like, can you quickly elaborate on what was on how does the normal distribution function work? Because I'm not sure I quite grasp the concept.
Well, we are going to do that next lecture before you do some practice with your class teachers and play a little bit with this table, and then we will definitely elaborate this in detail. That's not a 1 week story, absolutely. That's a pretty long story.
Oh, I see. Thank you then.
Yeah, you're welcome. Any questions?
Well, I have a question. Can you please elaborate on difference between PDF and CDF? I'm not sure that I get it.
Well, the CDF stands for the probability of the case that your random variable is less or equal to some threshold. So it's a probability that you are lower or equal to some threshold. That stands for the CDF. And PDF stands for the probability at the point. So F capital is the CDF, and it is defined as a probability being equal or being less or equal to a threshold. And CDF is a sort of, and the PDF is a sort of the probability at the point.
Yeah, but in the case of continuous distribution, we have PDF equal to 0, right?
No, because the PDF could be interpreted in 2 ways. If I say a probability distribution function, then this is assigned to the discrete random variable, and it is equal to fraction with outcomes. If I say about continuous random variable, the PDF is interpreted as a probability density function. If I said the probability distribution of the continuous, then it would be 0. But I never say probability distribution of the continuous. I say probability density function of a continuous random variable, and it's never 0. Well, it is modeled by these functions that we just presented.
So we have PDF for discrete distribution, which is probability distribution function, and we have probability density function for continuous distribution.
Absolutely.
And it's
Absolutely.
a function. It's a function which describes our curve.
Yeah, absolutely. Absolutely. You're totally right.
Sorry,
Okay,
what probability density function describes?
It describes the density of the probability of a continuous random variable. You may think that it's very close to the probability at the point. The probability density function may be interpreted as a probability at the point of the continuous random variable, but it's no longer that. So it could be greater than 1 up, as we discussed in one of the examples. It's kind of a function that models the curvature of a CDF function. Does it make sense?
Pretty
I will. I will post it. No problem about that.
Sorry, I have one more question.
Yeah.
Do we have CDF function in case of discrete distribution, discrete?
Yeah,
random
sure.
variable?
That's a probability, say, for example, that X is lower than 4. If you are rolling a die, then a CDF of 4 is going to be the sum of probability of 1 plus probability of 2 plus probability of 3 and 4 as well.
Okay.
Well, it seems to be quite strange and useless, but you definitely could do that.
Okay, so may I conclude that PDF says about single points on the graph or single measures, but cumulative distribution function accumulate on all the.
Yeah, absolutely. That's an interval estimation. You're totally right. Yeah, that's an interval estimation.
That's completely clear.
Great.
I'm sorry, I have one organizational question.
You're welcome.
So I spoke to our teacher assistant and she said that you are going to upload video records of our lectures. So is it true?
Yes, and videos been sent to the to Ksenia or Daria, and she's uploading it now to the YouTube channel, and you'll be sent with the link.
Oh, okay.
Unfortunately, only second lecture was missed because recordings were not stored at the Zoom cloud for some reasons. I am very sorry about that, but the rest 6 lectures are recorded, and they are, except this one, they are posted to the YouTube channel. Once we terminate, I download that recording, so it's going to be posted as well.
Okay, thank you.
All right, great. Anyway, that's good that we discussed some questions. I wish you to enjoy your weekend, to enjoy your Saturday, and hopefully we see each other in a week. Stay tuned, guys.
Thank you. See you.